David Lecomber. I'm the CEO and co-founder of Allinea. We're a HPC tools company, and we do not just debugging, but also performance and profiling of performance. So it's very much a gentle transition away from some of the performance talks you've had today. It's kind of weaning you off this like cold turkey. We're going from profiling through to debugging. I think I shared some of the lessons really from the previous talks. Some of the previous talks were really focused on the techniques more than the tools. So you really need to learn how to debug and profile, and then once you understand that, it's very easy to apply tools to those techniques, use the tools to apply those techniques. And obviously for my talk, I'm going to talk about Allinea's tools. So we've got DDT for debugging, which is available on all the systems you've got available today. And also I'm going to talk about the performance tools, the first of which is sort of like a benchmarking tool. It's a very quick, rapid report on what your performance looks like called performance reports, and then the profiling tool called MAP, which is source level profiling for people that want to develop code and optimize it. So they're all available and installed on Cooley, and we've got DDT on the Blue Jeans here as well. And if you have access to other machines, then there's a good number of the machines you're likely to have access to that will have all our tools on. So first, a little bit of motivation. You're all here to learn a lot about extreme scale computing, about how to apply your codes and port them, make them run faster, make them work correctly, and so forth. And it's a really important thing to be doing because, well, HPC systems are finite. They're very expensive, and they don't live that long. They're 3 to 5 years, and during that time, they've got to get some science out. That's why the machine was bought in the first place. So you're sharing a precious resource there that you really need to use wisely. And also, there's a bigger, more important resource than the HPC system, and that's you. So your time is finite. You've got a PhD to submit. You've got a project to complete, a paper to write, a career to develop, lots of things that matter to you. And if you're held up because your code is held up, because it's broken, or if you're held up because your code doesn't scale to the size of Mira when it needs to scale to the size of Mira, and you don't publish the result and someone else publishes the result before you do, it's not going to be easy. So it's really important to focus on doing things quickly in HPC. And that means doing good software and getting that software to go faster as well. So getting you faster, getting the software faster. And so hopefully through the tools you'll see today, have seen already and see later, you'll get a flavor of how to do that. So thanks, John, for sharing real-world examples earlier. And it's really a good thing to do is actually share when you get a performance profiling or a bug result or a bug fix and things like that. Tell people that these things are possible. So John, you mentioned changing just 2 lines and getting 30-something%. And this happens. It really does happen. So this example here of a bioinformatics code, we didn't quite just change 2 lines. We actually deleted 2 lines and got about 30% improvement. It turned out that there were many things to do to improve the performance and actually get a 3 times improvement, but 30% of that improvement actually came from commenting out critical regions in OpenMP. And if you've learned a lot about OpenMP this week, you've probably learned that there's a lot of options in there, a lot of things you can do, and sometimes the performance of them isn't that obvious. And what we found was an OMP critical region was actually making a very small piece of work in this genomics assembler basically go from one thread to the other in lockstep from one to the other all the way around, instead of just doing all the work on one thread and getting it over with. So these things happen in real life because people try and do these optimizations and they don't have the opportunity to profile them, see what happens. And genomics, they use codes, 32 gigs in a single process is, and lots of threads going through that. That's not unusual. It may not run on thousands of cores like you'll see in Mira and things like that, but it will run a lot of CPU hours. This particular organization, sequencing things in agriculture, it takes about 2 weeks to do a potato. So that's on 32 cores or something of that order of magnitude. So if you can knock that down to 10 days, you've helped them a lot. Deep learning, a bit popular at the moment, but of course, it's just another kind of HPC. It's matrix multiplications, lots of matrix calculations there, needs to be done efficiently. So we took Torch, which is the one that's used by Facebook, and an example on that, and we managed to speed that up by a factor of 5. And some of the techniques were very obvious things that you would do just from HPC, using better libraries, enabling vectorization through better use of if statements and so forth. And then onto a big debugging side, with a CFD code, we took that to 16 times more cores than it had ever been up to, and let them simulate something they'd never been able to do, because they fixed a crash that they couldn't have fixed otherwise without our debugger, but also improved the performance because they weren't getting vectorization when they should have done. So let's look at debugging, how it actually works in practice. You run your code, it crashes, you have an idea, or you should have an idea about why it's crashed. You call that a hypothesis. You insert print statements, you compile it, you run it again. You go round and round in that circle. And that still happens a lot. Although I'm here to talk about DDT, our debugger, the real competition for us is people who don't use a debugger at all, but use things like print statements. And that's not the best way to do debugging. Optimization is very similar. Some people will insert timers, they'll run the code, they'll analyze the result, they'll change the code, and they'll go round and round and round because they perhaps started changing the wrong piece of code. Okay? You can start at any point on this. Some people might just decide to change the code and then start analyzing it and so forth, but it's not a good idea. So some people miss out the inserting timers or the things that are going to measure stuff and just go around changing code and hoping it's going to go fast. You're making assumptions about what the performance problem is and then trying to fix that. And that's not really a good idea. And it's also not a good idea as machines get larger. If you want to machine in the top 500 in November, you'd better have over 10,000 cores because that's going to be the cutoff point. If you want to hit the top 100, you'll probably be okay with 100,000 cores, but there are a number of large systems coming into production by the end of this year. So the growth in the core count is getting there, and software is how people are going to actually start using that, and your job is to take HPC codes to levels they've never been taken to before and achieve things no one's done before. Several years ago, it was easy to get a 10,000 core machine. That's these here in 2011, 200 of them, 250 of them, and about 40 at 100,000 cores, and yet only 1% of application codes could actually use the full size of that machine down there, all of those machines there. So it is important what we're trying to do. So before I start on the techniques, well, I'd like to use a quote from I don't know who originally said it, but I first heard it from someone at Jülich who said, no one cares how quickly you can compute the wrong answer. So let's start with debugging. So it's always good to know what you're up against, and these are the categories of bugs that are out there. So, bore bugs, very, very steady, dependable bugs. The program crashes always in the same way. You've got a repeatable test case, it always does it. Brilliant, my favorite kind of bug. And the reason for that is it's something that's deterministic. It's very easy to fix. If you can reproduce something, you can fix it. Things like Heisenbugs, well, they vanish when you try to observe them. When you try to debug them, they're much harder, much, much harder. But you get things that are even like Mandelbugs, which are complex, obscure. It's such a piece of spaghetti code that it is chaos. It is chaotic. And finally, and this does happen, when you look at the code and you realize that can't be right, and then you realize it never worked. And of course, at that point, it'll never work again. The Schrödinger bug. Very good to know that. That helps to realize what the strategy might be for dealing with some of the bugs out there. Debugging is basically the art of transforming one program that's broken into something that works. But it requires thought. And there's a process. There's an acronym behind this. It's called traffic. But basically, a number of things that are important in how you handle bugs. Not just one bug, but all the bugs. So firstly, you probably don't just have one bug, and you might find several in the process of trying to fix one. So have a good system for tracking the bugs you've got. If it's just you working on your own, sure, a notepad will do. If you're working in a team, then there are plenty of systems out there on GitHub you can put issues in, things like that. So always have a way of tracking the problems. And then, once you've decided a bug to actually look at, make sure you've got a way of reproducing that bug. That's why bore bugs are so easy, because the reproducers are easy. Now, can you automate a test case? If you can prove that you fixed the bug without manually having to go through and do something, that is so much easier. And the other thing, it helps preserve your sanity as well. The number of times I have thought that I fixed something, but I realized I'd not done the test case, I'd not actually played that test case in my head through properly. You know, it's far better to have a system that says, yes, that's fixed, no, that's not fixed. Just look at an error code from your program, or if it's as simple as, does it crash or not? That's an automation. You can put that in a script. You can add that to your source code repository so that every time you build something, it checks that test case and says, have I properly fixed it? And that's good for the future. So once you've got those basic steps in place, start thinking about it, applying the mind and saying, where possibly could that infection be from? Now, if this program was working before and it's something new, then it makes sense to think, what has changed recently, for example? What am I doing that I've not done before? Am I on a new machine? Has somebody upgraded something? But more likely, has someone changed something? So once you've isolated down what could be some of those origins, you can then focus on one or two on them one by one, the most likely ones first, obviously, and then try and narrow down where that is, apply a hypothesis, say, yeah, if that was what had gone wrong, this would be broken now, therefore, ... And then you can say, well, that's not right, that's not valid hypothesis, this is, now go to the next one, and so forth. So it's very scientific, and then, of course, you're going to correct it once you've done that, and verify that test case that you wrote earlier is successful. There's a really good book, I have to recommend Andreas Zeller's Why Programs Fail, which is all about debugging, and it's got some great ideas in there. And it's far better to know how to debug than to spend a whole day sort of moving around inside a debugger, really trying to figure out where you are and what's going on. It's far better to apply a method to that and do it quicker. So what technique can we use for debugging? Well, there's a few. Automation is great. Test cases are the first step along the way for automation. And they also have the benefit of preventing you getting bugs in again in the future. You know, you've fixed it, it'll never be broken again if that test case stays there. Now, when you've got version control, which almost everyone uses these days for their codes, most of them, Mercurial, Git, Subversion, have a way of running a bisection. So if you know the code was working 3 weeks ago and it's not working today, you can actually do things as the command like git bisect, and it'll check out the version of code from halfway in that time interval, run it against your compile it, run it against your test case, tell you whether that's broken or not, and eventually it narrows it down through bisecting until it's got to the exact change that broke it. You can do that straight out of the box with tools you've already got your hands on available there to you with, and that's a problem solved very quickly without ever having to bring up a proper debugger. You've got observation. Now, a typical way of doing observation is print statements. But that's not very efficient when you get lots of cores. You've got to keep inserting things into your code, which potentially adds more bugs, or moves the bugs, especially if they're Heisenbergs bugs. Debuggers, they're the classic tool for this, because they let you look at exactly what's going on inside your code. Okay, you can look at variables, you can control things by making them move forward slowly and watching what they do. Inspiration, rubber duck debugging. Talk to someone about a particular routine and what it should be doing. And through that process of explaining how something works, you often find why it doesn't work. If you don't have anyone to hand, there is something called rubber duck debugging. There's a website all about that called rubberduckdebugging.com. Explain the source code to a rubber duck. And finally, debuggers are not just tools that just do observation of what's going on. Sometimes they have things built into them that are essentially magic. So DDT has got static analysis built into it for C and C++. So you get little hints against your source code when something might be the origin of a bug or is wrong anyway and worth fixing. We've got memory debugging, so that if you happen to read or write beyond the end of an array, the debugger will stop instantly and say, you've got a problem here. A problem you might not even know exists. Okay? So, a number of different techniques there. And interestingly, no one technique is perfect. You have to have the full suite. Okay? So, when you have a debugger, then this is all about identifying things like, what's the rogue behavior? What is wrong? Why is my program doing what it is? So DDT will take the stacks of every process in your job, merge them together. It's really good for identifying the outliers. If you've got 100,000 cores on one line of code and one on another line of code, that one is probably doing something wrong. The debugger will take you straight to the source code when there's a crash. Then from that, you can look at the variables and you can deduce how did that happen. Sometimes things are evident from the source. Crashes are real, those Bohr bugs, Heisenbugs, Mandelbugs, they can all give you that kind of answer. And a debugger really helps you to answer that, why did it happen? So this example here, there's a little graph here of what we call a spark line of a variable at this current point in time called myPE, and it's the variable of it across all of the processes in a job. This is actually the MPI rank, so it should have gone from rank 0 on the left-hand side up to the number of processes in the job. But there was a bug in the MPI implementation. It was a pre-release MPI implementation on a large system, and it got the ranks all the wrong way around, which of course was something no one would ever have thought to have checked, but the fact that it was immediately visible alongside the source code meant we jumped straight for it. I said, what's going on there? And of course we were able to identify the problem and fix it very quickly. But can you imagine having looked at a few ranks on myPE and them being correct, and you say, yeah, well, looks okay. Or you just got lucky and they were the right numbers, but when you actually see a whole pattern there, it's much more visible. So when you're doing lots of processes, visible really matters. You see up here, there's a really sort of squiggly pattern here, and that's jcall, which is a loop variable in this particular code. And because there shouldn't be a pattern, because when you pause processes, they're all at different points, that's okay. You see no pattern at all, really, just a very dense block of different values. But if you're expecting a value like a constant or a straight line, and it's not, that's really evident. So if I do a little quick live demo, I just fired up DDT from the command line, which is DDT. If you're on Cooley or machines like that, DDT, and up it'll come. And what you have is the choice of running a program from scratch or attaching to one that's already running. Or you can also look at a core file. So if a program crashes, sometimes, although often it's disabled on a HPC system, they will dump what's known as a core file, which is basically the status, the whole contents of that process when it fell over. And you can actually look at those and then deduce why. You can look at it at that instant in time. So let's do running a program. I just click on that. This is just running MPI on my laptop. We'll talk about bigger machines later. So I'm taking the core matrix multiply application, which is in the first example through that pack. Select the number of processes here. There are other options which are not necessary, so I won't bother turning them on. And I click Run. And it runs. So it starts the MPI run, and then it starts your processes. Now we've got 4 processes up. This is DDT's user interface, and obviously your source code right in the middle there, where you need to see it. There's a colored line here, which is basically where processors are at this point in time. If I hover the mouse, it'll tell me which processors are on this line. Okay. Oh, there we go, tooltips. And as you'll see, if I step a process, you can control processes with a debugger. You're not just observing, you're actually controlling. You can make them step, you can make them run as far as a particular line of code called a breakpoint. And these are all done by the buttons up here. And so if I was to press step over, it'll go over a whole line of code, and all of them are moving here in lockstep. You see, we've got this line moving. Up here are 4 processes. I've only got 4 processes in this job, and they're all colored red because all 4 of them are stopped. There's rank 0, 1, 2, 3. Down here are the stacks. These are where your processes are currently. Now, it's a very simple program. I've got 4 processes that are on, you probably can't quite, well, you definitely, it's much too small there. There are 4 processes all on line 96. You've also got a couple of other sets of threads here. They happen to be internal OpenMPI threads, so they're not particularly interesting. I'll just hide them out of the way. But you can see there are 4 processes and they're all on the same line. That's a good sign. Okay? So I can do things like step, step, and keep things stepping. It's all very easy to control. Step inside a function, step out of a function. On the right-hand side, we can see things like the current variables. There's one here called MR, which is my rank. It's diagonal from 0 up to the number of procs in there. If I had 100,000 processors, you wouldn't see 100,000 boxes. That would start telling you summary information, like 0 to 10,000 are doing this, the other 90,000 are doing something else. But these lines here, they scale, so it's always a 64-pixel wide bitmap that always shows a pattern. So I can see the current value of variables. I can drag things down that I want to keep an eye on more permanently down here, and it's always looking at what other processes are doing as well as the currently selected one. I can change which process I'm looking at by clicking the box up here. Okay, and if I set a breakpoint at this line here, say, and then I press play, it'll run as far as that line. You see it's done that and told me it stopped at a breakpoint. Okay, so that's not particularly interesting. Let's see, I really brought up a debugger to fix a bug. So if I press play, it's now encountered a bug. The program, it says that we've stopped with a signal FPE. Does anyone know what a SIG FPE is? Exactly, it's floating point exception. Basically, it's division by 0 more often than not. Okay? In fact, in this case, it says it's integer division by 0, and that's detected automatically by the processor. Okay? And then it's stopped, and the debugger then stops at that point. But it's not killed everything. Everything is there for you to take a look at and see why that happened. And right underneath, there's another problem as well. This one says there's a memory error detected, a null pointer dereference or an unaligned memory access. Also not good. So you can see I've got 4 processors that have all stopped because they're all colored red at this point in time. And if I go back to the stacks, I'll hide them out of the way. And this is showing that there are 3 processors on line 173, and there's 1 process on line 156, but actually it's inside function mmult at line 55. If you click around in that stack view, it will select one of the processors that's on that line and take you to it. So I've got 3 on that line, and you can see that here. But if I now click up here, I've moved to rank 0, which is on that line. It's got this far. And rank 0 was the one that had the floating point exception. So what's happened here, you could see, if it was a bigger font, if it were a bigger font, which is easily done, that I've stopped on this line, and there's a division here. It's size divided by n slices. N slices is 0. There's my problem. OK, let me fix that. DDT, you can actually edit the code in DDT. So let's see, why is n slices 0? Well, this is about splitting up a matrix, and I know that n slices should never be 0. So let me look above, find what n slices is. Well, it's MR it's the MR parameter when we called this. MR is my rank. That's a mistake. It should have said n proc. So let me do that, save it, and then I'm going to make it. I should configure my build, make, etc. Click OK. All right, let's build. Build the code. You can actually do this within your same reservation on your HPC system. So if you've got a quick fix, then you can actually test it out. It's always important to validate that you've tested the fix. You think it's fixed, it might not be fixed. You might have just found the next bug. So check it's fixed. It's great if you can actually do this. So you build, and then we restart. Obviously, we have to restart. So restart the session, and go run. Now, as it happens, that second bug where the other 3 processors were segfaulting is actually caused by the same thing. So I've actually fixed both of them now. There's the breakpoint from earlier. Now if I continue, it's run all the way through to exit, and it's a happy program. We've successfully fixed the first bug. So that's basically a demo of the things you can do with DDT. There's lots more to it: memory debugging, data visualization, lots more to talk about there, but I won't do that right now. I'll move on back to the slides. Some of my favorite features we saw the parallel stack view, great for finding when processors are doing something the same and when they're doing things different, because it's merging data. And the great thing about that is if you have 100,000 processors, it's just as easy to see what's going on as when you've got 4 or when you've got 400, right? The difference between 100 processors and 100,000 processors when it comes to debugging shouldn't be that great, because they're both large numbers that the mind can't handle. You need tools that aggregate things, and that's what DDT does. We've seen the automated comparison, another scalable feature that lets you look at the variables across procs. We can look through arrays and find nans, for example. Filtering on large arrays, it works in parallel across all your procs. If If you've got a NAND that's corrupt in your calculation, ask DDT to find it for you. The status thing, telling you whether processes are paused or not, how to step, play, and all those kinds of controls, all moving from being like small when you're looking with small process counts through to when you're looking at lots of processes. But another mode you might not have heard of is offline debugging. One of the problems with a large, when you first encounter your bug over several thousand processes, and you want to debug it, you'll probably find you don't have access to the machine at the time you want it. Luckily, machines are getting bigger all the time, so it's as easy now to get allocation of 10,000 processors as maybe 5 years ago it was to get 1,000 processors. But basically, very high core counts. No one's going to give you access to their machine right now when you're in the office. So you're going to submit it to the queue, and if you're not lucky, it's going to run overnight and you're not there to watch it. So offline mode basically lets you handle that situation. You ask it to debug in offline mode, and it creates a HTML file which basically looks like a debugging session. It's got all of the content in that the DDT GUI would show you, most important things in there, and from that you can deduce exactly where you crashed, and also the variables and things that were there when that happened. It's also got memory debugging built in there as well, so you can track memory leaks and things. So lots of things in there. And they're all scalable, parallel things. DDT's actually being used on sort of the largest machines in the world. You can use it on Titan at the moment, right up to the full size of that machine, or Blue Waters, or Mira. So there's lots of people using this for very large problems. Although even on those large machines, the vast majority of the bugs you'll come across are probably only on 8 to 16 processors. The first ones you always get are at much smaller scales. Having talked about debugging, I wanted to talk a little bit about optimization. Optimization is about a process to do this, and the most important thing to remember is this one: analyze before optimizing. It was back in 1974, Donald Knuth, who wrote one of the most important series of books in computer algorithms, my favorite being Searching and Sorting. He wrote that premature optimization is the root of all evil. And what does he mean by that? He means you can spend a lot of time optimizing a piece of code that only accounts for 3% of the runtime. Okay? You want to find the bit that's important. Spend all of your time there. And yes, be really aggressive about optimizing that. But don't waste your time optimizing too early for things that don't matter. Because there's a longer part of that quote, and it goes on to say that every time you optimize your code, you make it look a little bit uglier. It's less clear. So if something takes less than 3% of the runtime of your code, and it's nice and clear and everyone understands what it's doing, don't break it. Don't make it look difficult. Don't make it hard to debug and for someone else to work with in the future. So profiling is really important. Analyzing what to do and what's wrong. I have a picture here from XKCD. Sometimes you can spend too long deciding whether A or B is more efficient. So it's important that we're a little bit quicker in how we optimize too. So there isn't really, the process behind optimization is very obvious. You've got to get a realistic test case. There's no point optimizing something that doesn't represent what you're actually going to run. The cache performance of a 64 by 64 matrix is completely different than one for 2000 by 2000, okay? And it's different with 2048 by 2048 and a 2049 and a 2049. It's when you go over certain lines, cache behavior works differently. Well, the cache performance is different. So get something realistic. If you're working with big meshes and expect to run on that, if you're working on large core counts, that's what you need to look at. So profile your code, find the most obvious parts, the ones that are using the most CPU, discover what that problem is, then you apply the brain, then you bottle it. Essentially, I wanted to give people a view of what's the most important things when you're doing performance. We hear a lot about the Knight's Landing platform. We hear a lot about how you've got to vectorize. The reality is vectorization, it's very important to get that sort of 3-4x performance, but it's right at the very end. The first things you should be looking at are most likely I/O and the balance of the work that you have. If your workload is not balanced and some processes are working for others, it doesn't matter how much you vectorize because your problem is in the MPI and then in the balance because your work is, well, yeah. it's the workload, and you'll be sitting around in MPI all the time waiting for one process to finish. So it's important to do things in the right order. And typically that order is one of, firstly, profiling, analyzing, taking a good benchmark of what the performance looks like. Then if it's I/O your problem, deal with that first. Then if it's workload, do that, balance that. You can look at communication, optimize that. There are many things you can do to improve MPI communication. Memory patterns are more important firsthand than dealing with vectorization, for example. You can't vectorize if you don't have a good memory access pattern. So the first thing you want to know is, how good is my cache usage? And if you improve that cache usage, you're in a much better situation for being able to vectorize later. So it's helpful to just see kind of where you are on that path. And hopefully you'll be able to use that or share it with some of your colleagues when you get back to your desks and keep for the future. So I mentioned earlier the idea of bottling it. And what I mean by that is lock in the performance once you've won it. All it takes is someone else to be committing things into your code that slow it down piece by piece over time. And before you know it, those wins that you got, that great performance, isn't there anymore. So if you've got continuous integration where your code is running and being tested all the time, and as a number of codes are starting to do these days, that's great. Also record the performance when you're in there. Tie the results of that performance to whether that's a good build or a bad build. Okay? So record how performance is going. Then you can look in 6 months' time and say, that test case took 3 minutes 6 months ago. It takes 5 minutes now. I need to do something about that fix. So, lock in that performance. That's what I mean by the word bottling it there, keeping it, preserving it. And the same is true for bug fixes, which is what you're doing when you're adding test cases. So a little picture about Allinea's tools. I've spoken a little bit and demonstrated DDT, which is our debugger here. We've got a few more, and I'm just going to explain how these all fit together. We've got performance reports, which is an initial benchmarking tool that helps you to characterize what your performance looks like. That's aimed at developers, but also people who aren't developing code. Sometimes you can improve the performance of a code just by changing how you run it, how many cores you're on, how many threads you're on, running on fewer nodes because you're not using all the memory and it's not scaling. Those kinds of things. Lots of decisions you can make. Or you might discover vectorization isn't there and it should be, so change out the compiler or find some other, find another library that does something. Lots of things you can do that don't require development, and so put that, and it's also a really good tool for showing people what your performance looks like. It also spits out information through open interfaces like JSON, if you want to program with your performance results. But then when you've looked at your code and decided what the performance looks like, we've got map. So map is our profiler. It just looks like DDT, and I'll show you in a moment. And the reason for that is it's all within one common environment where you can actually develop, you can save your code, you can commit it back to your version control system, you can compile, you can debug, all within one thing. So Forge is the environment that is basically DDT and map together, which lets you do everything you need to do in HPC. One of the hardest things about tools users perceive about tools is getting started. So by having DDT and map share the same environment, it's much easier because when you're configured for DDT, you're already configured for map. So if you already know how to debug, you can profile at the same time. And I'll show you how that really works in practice. So firstly, performance reports, the tool that helps you understand, benchmark, characterize performance. It's really helpful to help people realize what performance they might be missing. And the way we do that is through a single one-page HTML report, graphical, gives you the information, and you can share that. You can email it to people. They can take a look at it, and they can understand what's going on. And so we're showing people performance, show, don't tell. And we can see this particular example. This is your code on -00. It's all memory accesses, no vector operations, so there's no vectorization here, and it's all scalar operations, so your regular floating point multiplications. And it gives you advice at the bottom. The per core performance is memory bound. Use a profiler to identify the time-consuming loops and check their cache performance. Okay? And so then it naturally leads you to the question, vectorization, that sounds good. How am I going to get that? Okay? And that's one thing we've deliberately not done is use terminology that someone who was writing or creating processes would do. We don't talk about things like out-of-order instructions, pipelines, pipelines and time per required instruction. We talk in the language that matters to scientific developers, which is, where is it? Is it memory accesses? Is it scalar cut ops, vector ops, single corner, etc.? Okay? It gives you the advice. Within that, this is what one looks like. You can see things like CPU usage, memory consumption, so what your maximum footprint of memory is, for example. Threads, whether you're losing time to synchronization, even energy, how much energy is used in a simulation. And obviously MPI. And if you look at the workflow, moving back now to the development tools, whenever you're doing HPC development, there's profiling, there's optimization, there's running it, it's broken, you debug it, you code again, you profile, you optimize, you do it. It's always this circle. And that's what really inspired us to bring the two tools together, because we thought that people would they would be profiling to find performance bottlenecks, and sometimes some things that are performance issues are actually properly bugs. It could be that require you to look inside the code. So if workload is imbalanced, one of the best ways to discover why is to use the debugger to watch why variables are of particular values and why the partitioner is doing what it's doing. And then so from the map, you could then flick straight to DDT and look at how that's behaving. So it makes sense to bring these things together. We've done a few things to make life easy for people using HPC. We know that you don't have a cluster in your office, most probably. You're working on a remote system. Especially leadership facilities, you could be thousands of miles away from them. And there's nothing more painful than things like X servers and trying to get graphical interfaces back from one side of America to the other, or transatlantically. So we've got DDT and Map, Forge, they all have this same remote client, this GUI. It's actually the same GUI if you're, it's the same binary package if you're running on Linux. It's actually got the tools inside it, but if you're on Windows or Mac, it's a remote client that connects to everybody. So that's for Linux, it's OS X, Windows. It can handle multiple hops SSH. Basically, it connects. All of the graphical traffic is then happening on your laptop, and the amount of traffic it's sending back and forth over the Atlantic or over the country, over the continent, is much smaller because it's not graphical. It's just step these processes, get these results back, and so it's much quicker. And you're also, it feels like you're working right there locally. It works with all the security things. And you don't need a license locally to have that. It's all up on the supercomputer. So that's the best way, it's a recommended way for working here at Argonne. Map, our profiler, this is what Map looks like. Very similar to DDT's GUI. I won't do a live demo because of the time. But you can see source code, and on the left-hand side, showing the time being spent in particular lines, green being for compute, and blue being for MPI. This doesn't have MPI at this point. You can see things like where your vectorized instructions are over time. So this is from the start of your application through to the end, and it's running across all the processes, merging the data from all the processes, and it gives you a top-down stacked view of where that performance is going. So if you find 50% of your performance in one particular place, go for it. Go and speed that up. And what Map does is actually, it's very scalable. It actually doesn't try to record every message, like where it goes from A to B or B to A and things like that. It doesn't do that. It samples. And John spoke about sampling versus tracing earlier. Map does sampling. It looks at where things are every time it takes a sample at particular intervals, and it records that. And it also throws away information when it's got too much. It's only interested in the things that are going to cost you a few % in performance. So it merges all that data up, and it's all scalable, which gives you data files that the biggest one we've ever seen has been about 50 megabytes, which is tiny for performance. And that's for doing 10,000 procs on large codes. We aim for less than a 5% slowdown in your code, so you can actually profile real test cases. There's no point profiling small test cases. I mean, there's some point, but not enough point. It's not going to help you with a representative large-scale problem. So we had to make it fast, so it's 5% slowdown. People don't like the pain of recompiling their applications, so we were very keen to do it without instrumentation, without recompilation. On a Cray, you have to relink, but that's changing soon. But above all, because we're sampling, we're focused on time, and we don't, therefore, prejudge what the problem might be. We're not prematurely optimizing either. We're saying, this is what the problem is. It could be MPI, it could be threads, it could be I/O. But fundamentally, if there's a problem, map will show it, and you'll see it next to your code. You'll see that's where 10% of my time is going. Then you'll look at MPI and say why. Here's an example. This is just a 512 proc example. It was a code that ran slower on a brand new machine than people were expecting, a CFD code. Over time, the blue line up here showed a bit of MPI. You can't quite see, but there's a spiky green here. So compute is happening. It's kind of going in a sawtooth-like pattern. Okay? And you can see, so next step. We zoom in on that a little, make it a little easier to see. But we could look right down to the stacks. And we saw at the bottom of the stacks that periodically we were seeing these blue bars of MPI popping up. And we could see right down to the source line, it was PMPI file at. So even though MPI I/O is better than no I/O, or better than normal I/O, it's still not a perfect solution. It's still a scalability bottleneck. So the less you do of that, the better. And so what we'd identified was that these periodic losses of performance were every time it was taking a snapshot. So the very simple fix was just to reduce the periodicity of the output. We didn't even need to develop a fix there. So that was an example of something where you can make a code faster without changing anything. That was lucky. But still it was slow. And what we found was there was no vectorization. So this, over time, these bars here would be showing you floating point instructions, which are here. That's a line. If you can't see it at the back or even at the front, it's going up and down quite a lot. But the vectorization was right down at 0 all the way across over time. You can zoom in on time parts, but that still wasn't helping us to understand why it wasn't vectorized. So what we did was we switched to a debugger. But the good thing was we were still connected to the remote server because they're sharing the same user interface. So going straight from profiling straight to debugging. And it was configured because it had all the settings from profiling. And that was it. We were then able to fix it. What we found was that a macro had been disabled that would have enabled the SSE path through the code. Okay, an inadvertent bug inserted. If you are interested in how scalable things are these days, we do have active users going well over 100,000 cores quite regularly. We've been up way beyond that, and some of our customers have been way beyond that too. In terms of profiling with map, I know of cases, and I know I've used it at over 50,000 cores. I don't know if anyone's gone any higher than that. Scalability was great. They didn't slow it down by more than 5%. But so we're very happy with how that worked out, and it gave us some good answers that let us actually improve the performance of that code. But we have a lot of people just doing this on single desktops too, and you'll find our tools on a lot of the machines there. Fundamentally, they're all fast enough that you can get your job done. I've mentioned some of the good things inside the tools. Offline lets you do things like alternatives to printf. Watch points to stop on a variable change, static analysis to show you the errors inside your code, reading and writing beyond the end of arrays, and finding memory leaks as well. So if you're exhausting memory because you're not freeing it, that's there. Find the peak memory with map, find the peak memory use, fix an MPI imbalance, remove I/O bottlenecks, we saw that one earlier. And also you can see where you're spending more time in memory. So the instruction things would show you which parts of your code were doing more memory access than actual floating point. If you've got bad memory patterns, you can easily spend 75% in memory and less than 25% in actual floating point. So that shows up like a real canary in the mine here and helps you do all that restructuring. Instructions for how to get started. We'll be doing all this later. The slides are available, and I also sent an email around earlier. But Argonne does a great job of installing the tools and supporting them, and the instructions are all also visible out on the web there. For Mira, for example. For Cooley, it's exactly the same. And on Cooley, we've got the performance reports, so that snapshot tool, and we've got map, and we've got DDT, so you can see the whole thing together. Again, these instructions are also in the slides on the website. And we've got a trial thing that's also in the email. And that's it. So thank you very much for watching. I hope that's been useful, and hope we're going to have some fun later today and improving some codes and fixing some bugs. Any questions?
So you talked about how a certain piece of code, you said I'm not getting maximum performance out of it. does Allinea like give us hints about what kind of performance should we get given a piece of code?
What kind of performance could you get?
Well, yeah, we know like there is a maximum flop, so and as was mentioned earlier, like most of the application will never hit the maximum flops. But given like the information you got about the memory access and flops, so can you just like, okay, we need to push. Can you like give an estimate like how much performance can be got?
The maximum potential you could get out of a code. That's not possible really with a tool, because the tool tells you what the current performance is, not what it could be, and not everything is amenable. You can't always make everything vectorized. It's just the nature of it. I did see someone last year who gave a talk. He'd been using our tools. He used performance reports, and it was a seismic RTM code. And there, it's like a 3D stencil with multiple points from all of them, and the pattern was kind of terrible. And with performance reports, he was able to say, right, initially my memory usage, memory time, 80% of the time is in memory, and 20% was floating point. I'm not going to vectorize, because there's no point. It's memory I've got to sort out. So then he restructured things, used standard techniques to do that. And now the difference was 50% memory, 50% floating point. At that point, it made sense to go into vectorization. But after he presented the two different before and afters in his slide deck, he then did a final one which showed how he calculated the best performance. And what he did, he knew his operations. He knew if he was perfect, if he'd made that memory access pattern perfect, there were, let's say it was 12 multiplications required. And if he was getting the maximum throughput, because he knew the clock speed, and he knew what the vectorization performance, he could say, this is what I can get. And what he found was that he'd managed to achieve, performance reports told him the balance was whatever it was. And he said that corresponded exactly with the theoretical perfect. So he knew his job was done. So sometimes you can.